Hello, my name is Shibu Lee. I'll be your CFI for today, and today I will be teaching you about pressure altitude and density altitude. The study materials for today's lesson is going to be the PHAC Chapter 4, the FAA safety brochure on density altitude, along with the Cessna 172 Sierra Model POH. Now, before we get into pressure altitude and density altitude, we first have to understand atmospheric pressure. Air is very light, however, it still has mass, and therefore it's affected by gravity. We feel this force from all directions, and we call this force atmospheric pressure. Atmospheric pressure decreases as you increase altitude because there is less air on top of you. Now, to understand this, I like to utilize a swimming pool analogy. So let's say that we are sitting at the bottom of a swimming pool. The pressure that you would feel would be very immense because of the weight of all the water that's on top of you. Now, as we start to swim to the surface, the pressure that you feel would decrease because there is less weight of the water on top of you. Air in Earth's atmosphere works in a similar way. In fact, the weight of the atmosphere at 18,000 feet is just 1/2 of what you experience at sea level. Now, the pressure of the atmosphere in a given area is always changing. So we came up with a standard atmosphere that we can compare all those changes to. Standard atmosphere at sea level has a pressure of 2,992 inches of mercury and a temperature of 15 degrees Celsius. Now, we know that the atmosphere changes as we change our altitude, and we call that change lapse rate. Standard lapse rate says that every 1,000 feet you gain, you will lose 1 inch of mercury in pressure, and you will lose 2 degrees Celsius. So at 1,000 feet, our pressure would be 2,892, and our temperature would be 13 degrees. At 2,000 feet, our pressure would be 2,792, and our temperature would be 11 degrees, so forth and so on. One more concept I want to introduce before we get into pressure altitude is SDP, or standard datum plane. Now, standard datum plane is described as a theoretical level where the weight of the atmosphere is 2,992 inches of mercury. The definition of pressure altitude, simply put, is just the height above the SDP. Now, depending on the given pressure of the day, the SDP may be at sea level like in a standard atmosphere, could be above sea level, or it can even be below sea level. So let's use this example. Let's say the local barometric pressure for today is 2,792 inches of mercury at sea level. Using our knowledge of standard lapse rate, we know that if we go down 1,000 feet, we will gain 1 inch of mercury. And if we go down another 1,000 feet, we will gain another inch of mercury. Right here, our pressure at this level is 2,992, or SDP. And we know that the height, or the definition of pressure altitude, is the height above the SDP, so our pressure altitude here would be 0. If we went up 1,000 feet, our pressure altitude would be 1,000 feet. If we went up another 1,000, our pressure altitude would be 2,000 feet. So even if our true altitude is 0, our pressure altitude would be 2,000 feet, or the height above the SDP. So how do we figure out what our pressure altitude is? First, we can set our altimeter to 2,992 and read the altitude that it's showing. This is because the altimeter is essentially just an instrument that detects changes in pressure, and now we've just set it to SDP. Another way we can do it is utilizing the pressure altitude formula, which is pressure altitude equals 2,992 minus the current altimeter setting times 1,000 plus field elevation. Now, before we get into density altitude, we first have to understand what factors affect air density and how that affects our aircraft. We have 3 factors that affect air density, and that's going to be pressure, temperature, and humidity. Starting with pressure, imagine we had a can of air and we compressed that can of air, right? We added pressure to it. That can would have the same amount of air inside, but now it's taking up a smaller amount of space, right? That air would be a lot more compact, it would be a lot more dense. So as pressure increases, density increases as well. As pressure decreases, our air density will decrease. Next, for temperature, we know that heat causes air to expand. There's the same amount of air molecules, but now they're taking up a larger amount of space. So as temperature increases, density will decrease. Lastly, for humidity, we know that water vapor is lighter than air. The more water vapor there is present in the air, or the more humid the air is, the less dense that air will be. So how does air density actually affect our aircraft performance? It's going to affect the lift, thrust, and our engine performance. So we know that lift is produced by moving air over our airfoils. If the air is less dense, there's going to be a lower amount of air molecules moving over the airfoil, therefore reducing the amount of lift that we can produce. We know that thrust is created by a propeller, which is essentially just an airfoil that creates lift in the horizontal plane. If the air density is lower, there's a lower amount of air molecules moving over our propeller, therefore reducing the amount of thrust that we can produce. Lastly, we know that air is one of the essential ingredients that we need for our engine to run. As you can imagine, if the density is low, there's a lower amount of air molecules available, therefore decreasing our engine performance. This is true for naturally aspirated engines like the one that we have in our Cessna 172. So we understand air density, but what's the difference between air density and density altitude? Density altitude just describes the altitude at which our plane feels like it's flying at. Density and density altitude are inversely related. So if density is very low, our aircraft would have bad performance. It would feel like it's flying at a high altitude, so we would have a high density altitude. If the air density was very high, our aircraft would have very good performance. It would feel like it's performing at a lower altitude, so our density altitude would be lower. How do we actually figure out what our density altitude is? Well, the definition of density altitude is going to be pressure altitude corrected for non-standard temperature. So we would use the density altitude formula, which is going to be pressure altitude plus 120 times outside air temperature minus ISA, or International Standard Atmosphere temperature. Big performance factors are affected by density altitude. We can take a look into section 5 of our POH. Right now we're looking at the short field takeoff distance. So let's start at sea level and 0 degrees. As we move up 10 degrees, we can see that the ground roll and the total distance clear 50-foot obstacle increase by approximately 100 feet per 10 degrees. If we look at pressure altitude, every 1,000 feet that we gain, the ground roll and total distance also increase by about 100 feet. That's a lot of runway and total distance that is increased with an increase in density altitude. As you can notice, these tables don't factor in humidity. That's because humidity has the least amount of impact on our density altitude. However, the FAA safety brochure on density altitude recommends that we increase our distances by 10% if we're in a very humid environment, and that we have